Teman-teman, ini yang slide pertama ini sebetulnya aku udah punya slide-nya, tapi mikir-mikir lagi soal audiensnya, terus mana yang aku mau masukin, mana yang enggak, aku ganti total, aku tulis tangan. Soalnya ada beberapa bagian yang aku rasa kalau kita masuk ke sana nanti malah keluar dari jalur dan kita kehabisan waktu. Monggo, silahkan.
Okay, good morning, everyone. Welcome to the 8th days of summer school. For today's lecture, 4 sessions will be
Conducted
by Mr. Frederic Ezerman from Lanjar Technological University. Yes.
Hello.
Okay, so very good morning to everyone present here and also online. I'm very happy to be back here in UGM to meet with many people I know from a way back, and I have a good number of collaborators here, so very happy to be here again. So here is what I propose for today. For our friends who are joining online, welcome. Today, I am proposing 2 topics. The first one, I want to go through with you the several number theoretic aspects in Shor algorithm. Maybe most of us have heard of Shor algorithm. This is the algorithm that, this is a quantum algorithm. That means to run this algorithm, you need a quantum processor. We'll touch a little bit on that, the difference between quantum and classical. This algorithm is very famous, but it's also difficult to go through. At least it takes a lot of technical details to digest before one can say, okay, I understand what's going on here. Many people refer to this algorithm without ever having seen anything about it. So what I want to propose for us this morning is we are going to look into some of the number theoretic aspect of the algorithm. My apology for not preparing a prettier, a more beautiful slide. I had to adjust quickly and to the material and to the audience. I hope my handwriting is legible enough. If not, you can ask me directly what that one is. Okay, roughly I have 90 minutes, including the question and answer session, right? Okay, so good. So what I propose today in the morning is we look into this, into the classical aspect of Shor algorithm. Okay, Shor algorithm is a quantum algorithm, but it has mostly classical components. Only one crucial component is quantum. I'm not going to discuss the quantum portion because to do that I need to go back quite a bit. But I want to give a rather complete picture, a rough picture of what Shor algorithm contains, and then from there we can see how how number theory plays a very important role. Okay, some of the details may take time for you to digest. Okay, may take time for you to digest. So I'm just writing it down there. Later on, you can try your hand on it, checking it one by one. if you discover that it differs from my part, do not dismiss your work immediately because the mistake might be mine. Okay? So I'm not discounting the possibility that I make mistake in my computation, but at least the main ideas and the flows, I'm pretty much convinced it's okay. Right. That's what I propose for the first session. The second session, I will touch on something a bit different. Still number theoretic. I trust you have gone through an introduction to coding theory with Professor Putranto. So I'm not going to go through all those basic material again. Okay, I hope those online and those who are here not quickly being discouraged, because you might be thinking, wow, today is going to be technical. Yes, it is going to be technical. It's a summer school, right? It's a research school. So be ready for going technical. Okay. I'm not responsible of setting the question for you, okay? I leave that to the organizer. But today's session will be technical. Yes, it will be technical. I will blame the organizer for inviting a researcher here. Not a teacher. I'm not much of a teacher. I'm more of a researcher. But I try to make sure that we cover all the important steps. So my hope is that you don't feel discouraged, but you feel encouraged because, hey, this is really a technical material. It is not easy to digest, but it is digestible. Okay, it is digestible. It's not like it's not beyond us. It's not beyond us. Actually, Shor algorithm is understandable by those who have studied introductory number theory. That's enough. Introductory number theory is enough. Okay. So it's not something like super difficult, no. My point for the first session is that when we are talking about cryptography nowadays, when we are talking about security nowadays, we must be aware of what kind of attacks are available for the adversary. Because when you say that the system is secure, when you say that the system is making sense to be used, you must know what kind of adversary you have. Okay, so that's a rather long introduction, but I hope it motivates us enough to see that yes, today's session with me will be quite technical. Yes, you might not be able to catch up with some of the details or most of the details. That's fine. It took me many months to really understand this. Okay. But what I would like to share is the hope that you will be able to catch up with the main flow of the argument. Okay, the main flow of the argument, because then you can continue on your own and look into the details of the material. Last, before we go into the material itself, into the content, please feel free to disrupt me and stop me if you have questions. We do not have to finish the material. It is better to understand everything up to a certain point rather than going through all of this and you leave the room completely blank. Because then we don't achieve anything. Okay, so feel free to just stop me. Please stop, and I want to clarify on this. This applies also to those attending online. Please feel free to stop me. Please feel free to ask your questions. I think somebody, maybe Pak Uha, is on hand to pass with the question. Ready? Anyone wants to go for toilet break first, coffee first? Well, make sure you're ready. Okay. I guess I'll turn off my video. Oh, okay. Yeah, exactly. So I'll just stop my video here, and I'm back to sharing this. Okay, so I think that's better. for everyone? Okay, let's get ready then. I get my energy by standing and walking. Sitting down like this, I feel like constrained. All right, so I'll start with a quote from Gauss. This is from his famous work, of course, Disquisitiones Arithmeticae. The translation from Latin is not mine, okay? I don't know enough Latin to translate. This is the English translation, quite nice. So the problem of distinguishing prime numbers from composite numbers and of resolving the latter means the composite numbers, into their prime factors is known to be one of the most important and useful. And why I'm putting this in boxes? Because I believe that's what mathematics is. It's important and useful. Many people say it's important but not useful. They just don't know it yet, or they don't understand enough about what's going on in their life. I'm sorry, I'm proud to be a mathematician. So, see, it's important and useful. Okay? And then he continued, it has engaged the industry and wisdom of ancient and modern geometers. Those days, mathematicians are known as geometers, or those who calculated distances. Okay, nowadays, geometry is something else. Okay, so it would be superfluous to discuss the problem at length. I suppose every one of us agree, we know the problem. Okay, the problem is that factorization. Okay, further, the dignity of the science itself seems to require that every possible means be explored for the solution of a problem so elegant and so celebrated. So he set up the tone very nicely, and I think this still applies a few hundred years after he wrote this down in Latin. See, this factorization problem and the study of primes, these are very, very important that we are still doing it now. And in the modern era, when we are talking about computational power, then there's another concern coming up. It's not just how to settle it, but how to settle it efficiently. Because, hey, I can do factorization, yes, but you wait 20,000 years. Who has time to do that? I mean, forget it. I want it now. I want it yesterday. Okay, so here we go into the realm of not just computation, but also complexity. So I'll touch on a little bit about, computational complexity without giving you introduction to computational complexity, okay? We're not going to have time for that. So you just have to trust me. When I tell you that this is efficient, you trust me. It's been done. We know that this is efficient. Okay. So today we focus on time complexity. And now I'm going somewhere else. Okay. Feynman keynote lecture. So let me check where that one is. I think it's here. All right. So this was something that I give a talk to here, but I'm going directly to different slide. Here. So what are all this business? Hey, what happened? Oh, okay, now it's coming up. What are all these talks about quantum computing? What's the deal? What are we trying to do in quantum computing, really? So you must blame this guy. This guy is the one to blame. So anyone of you know who this one is? It's Richard Feynman. The Nobel Prize laureate in physics. He passed away already. So back in the 80s, he was dealing with the problem of simulations of natural phenomena in computers. And what disturbed him the most is the following. The law of nature as we know it right now, as the way we understand it in physics, is not just electrodynamics, not electromagnetism. But the best physical theory we know right now is quantum mechanics. But the computers we have, this one runs on what? On classical physics, right? We use electricity, we use currents, we use zeros and ones, representations of on and off. So this is digital computer, which is not running on quantum mechanics. So then he has this very, very fundamental questions. Guys and girls, let's make quantum computer. So what is quantum computer? Well, quantum computer is a computer that runs on the foundations of quantum mechanics. So how do we make it? I don't know, he said, I don't know. If I know, then I will not lecture on this, right? So he said, let's do this. So he said, this quantum computer will not be a Turing machine. It will not operate on the church Turing foundations in logic. It will need to switch into a different logic. And then he said, okay, he's a Nobel Prize winner, so he can use words like this in lecture. Okay, don't use words like that in your lecture, especially in Indonesia and well, in Southeast Asia in general. But he's a Nobel laureate winner, so he's a rather colorful personality, so he used words like that, and it goes into a journal. It's actually published in an official journal. Verbatim, he said, "I'm not happy with all the analysis that go with just the classical theory because nature is not classical." Censor. If you want to make simulation of nature, you make it quantum mechanical. And it's a wonderful problem because it's not easy. It's not easy. So if you watch in the news, you read in the media, hey, now we have quantum computer, okay, the era of quantum supremacy is coming. Okay. Relax. It is not that easy. Okay, it's not that easy. How do I know that? I've been working in quantum error control coding since my third year as an undergraduate. That was a long time ago. And we are still unable to control even medium-sized processor. You might be asking, what about those Google and IBM, Rigetti, quantum computing and stuff? Oh, forget it. That one cannot run shell algorithm, for sure. We need to be able to do a lot better exponentially before we can even dream of implementing shell and growth. Okay? So this guy is the one to blame. He's the one making all this problem. So then we started talking about how to create first, how to represent information in quantum form. That's important. Because when we talk about digital computing, right now we have every strike in your keyboard is translated into 8 bits, right? Into zeros and ones. And those zeros and ones are interpreted by the digital computer as either the circuit is on or off. And then it has logical operation like OR, XOR, and so on and so forth, right? So we have all of these mechanisms. Now, when we go quantum, what happened? We don't have 0 and 1 anymore. We have things called entanglement. We have a lot of weird stuff going on. Okay, and that means the circuit will be different, the operators will be different. And then the next question is, how do you realize this engineering-wise? What do you use? Photons. How do you deal with photons at that level? So that opens up an entire area of studies. But since we are here mathematicians, we don't know how to do engineering. We'll just leave that to our more clever colleagues in engineering, and we go back to the number theory. Okay? Because, that also will help them. So we supply, it's like a go back and forth. But here is the original plan. So the original plan of quantum computing really does not see this as part of breaking ciphers, creating new ciphers, and so on. It's a very generic problem. Let's make a quantum computer. What can that computer do? That's another issue altogether. Okay. So now that's the one that we are going to go through today. That paper. Okay. So now, if later on you have time, you have energy, or you are bored, and you say, I'm going to torture myself. I'm going to exercise. Okay. Pick this paper and try to read it. Now, actually, this is not very difficult, right? Our class 2 semesters ago, we looked into this, right? Yeah. So it's okay. I mean, early master student can read this. Not very difficult. Difficult or not?
Yeah.
It took me a few weeks to digest the flow. But this is an excellent paper. Really breakthrough. And Peter Shaw got a lot of award for this. So that's the original paper. Now let's look at the part I highlight, okay? So it says a digital computer is generally believed to be an efficient universal computing device. Okay. But the computation time, when we consider the efficiency factor, is at most a polynomial factor. This may not be true when quantum mechanics is taken into considerations. Okay, the paper considers factoring integers and finding discrete logarithm. 2 problems which are generally thought to be hard on classical computer has been used as a basis of crypto systems. So now what he said is this: efficient, randomized. So those two, you must remember, efficient and randomized. These are important, okay? What are they? Efficient and random. Given for those 2 problems on a hypothetical quantum computer, you see, this guy is really precise. He said hypothetical quantum computer. This paper was out in 1997. Actually, the work started being known in 1994. It was still a draft, a conference draft, but people start reading and very excited about it. So, see, this algorithm takes a number of steps, polynomial in the input size. That's the language of computer scientists of saying this is efficient. See, saying efficient, they say number of steps is polynomial. But in the language of computational complexity, this one is saying this algorithm is efficient. Why? Because it grows only polynomial. It doesn't blow up in terms of computations. So this is the one that we're going to look into today. Now, how does that affect? What happened here? This was taken from Nature, 2017. Now I think there is a slight differences in the fine graining of the analysis. But if you look at this table, forget Grover algorithm for now. I'm not going to discuss it. But let's consider Shaw. See what happened here? You recognize these friends? This is the one that you use in your mobile phone and in your credit card chip. If you have them, that's this. Usually the curve is P256 if you use devices made by American Standard, okay? But I mean, the curve, you can choose other curve. But essentially, everything is broken, whichever curve you take. Now, RSA is the main system that protects our online banking. All right, so you see why a lot of money is put into this? Because it deals with a lot of money. So if you want to protect a lot of money, you don't mind spending quite a lot of money. Otherwise, your asset, which is this super big, a lot of money, can go. So money is a big motivation in research. And this is how we should market ourselves, you know, as businessmen. You have a problem, I can help you solve the problem. That's what cryptographers market themselves, actually, to the industry. To this. And the military is, of course, very interested because everyone is using this system. They can break it. They can read everybody's business. They can read other countries' business. They basically become the ruler of the world, as it is. Then people will go back into communicating without computers, more localized. But you see, this is very serious. That's super, super serious. Luckily, what Richard Feynman said is still true. It's not easy. So we are lucky. So I'll stop there with this detour. I hope it adds to your motivations. Any question? Now I'm going back to my lecture note because we still have quite a lot to cover. So I hope you understand the importance of what we are going to discuss today. It's not just a very interesting and difficult mathematical problem. It is also a problem that affects the life of everybody using modern communication system. So next time somebody tell you, oh, you're a mathematics student, you're computer science, theoretical computer science, what do? You can answer that. You cannot convince them, confuse them. Okay, so yeah, these are the basic facts. We use the presumed difficulty of factoring as a foundations of much of our PKI. Last night, when I was reviewing this again, I was like, PKI, that's something sensitive to say in Indonesia. So then I have to write there, okay? It's a public key infrastructure. It's not a political party. Okay. Just so that everybody clear, we are not talking politics here. It's a public key infrastructure because in the cryptographic circle, it's very often we use PKI. Everybody understand what PKI is. Okay. So much resources, a lot of money is spent on this problem. And now this is the note that I have. I've shown you the situation now. Okay. So here is the focus of this session. The technical, that is the number theoretic aspect of Shor algorithm. Okay. I've shown you Shor paper and the table of the affected protocols. Essentially, everything which is based on elliptic curve is gone. Everything which is based on factoring, everything based on discrete logarithm is gone. So you might be asking as a student, should I learn those things? Yes, you should. Both from the perspective of design, but also from the perspective of how to break them. Okay. And they're still in use until quantum computer of sufficient scale become reality. Okay. So what is out of scope? I'm not going to talk about quantum engineering aspect because I don't know much about it. I know people who know about this. I can ask them, but I don't know about it, so I'm not going to talk about it. So number two, I know quite a bit about it, and I can actually explain to you, but it probably will take another session. So I'm taking it out. Because if I want to explain to you quantum Fourier transform, we need to go back into quantum mechanics a little bit, okay? Qubit entanglement, state preparation, unitary operators, all those things. So you might be asking, so then we are not going to discuss Shor algorithm. Shor algorithm is a quantum algorithm. Yes, we are discussing Shor. We will focus on the classical aspect, and I will mention to you what is that algorithm doing in the quantum setup. Actually, only one component is quantum. Everything else is classical. Okay, so our summer school theme is number theory, so we should stick to it. Any question so far before we climb up? And yeah,
I was wondering if it is possible to zoom in.
You want to zoom it a little bit? Zoom out or zoom in?
Zoom out.
Zoom out. You want it like this?
Zoom in.
Zoom in? Okay, you want zoom in. Okay, all right. Let me see. It should be okay. Yeah, this is the best I can do because. Any other questions? Yeah.
Maybe this one is a bit stupid question. Because when you know that quantum computing can run the Shor algorithm, so I agree with factorization and everything we can. But because since it has a very high power, is it possible also if maybe if we run it on some lattice based or something like that, also will be much faster, right, compared to one computer that we have right now. So is it possible also for lattice based and something like that, also in danger?
Okay, very good questions. I have partial answer to it. The other, we don't really know. So let me start with what I know. Okay. So the gist of the question is okay. So this quantum computer very powerful, right? So it breaks discrete log. It breaks factoring quickly. Will it not break lattice based, encode based, and all of the others? So far, what we know, Shor algorithm and Grover algorithm and a few other algorithms that can be used to perform cryptanalysis, they attack a certain structure. They attack a certain mathematical structure. And today, my task is to show to you which structure is being attacked. Okay, so this is why then we are looking into all of these other structure, lattice based, code based, isogenies, because we want to say, well, if I want to defeat Shor algorithm to make it ineffective, what mathematical structure should I use? Before we fix something, we need to know why the previous one is broken, right? And this is why today I want to go through why that one was broken. Okay, so that we can then say, okay, that one is broken. Why was it broken? Because of its structure. So now let's avoid that structure. Okay, so lattice based, code based, they avoid the structure that I'm going to show you. It doesn't have this structure of abelianness. Okay, the one that we use for discrete log, elliptic curve is an abelian group, right? If you look at the points there, you choose the points well, then it will form a group. In fact, it's actually a cyclic group. Now, with factoring, we are going to transform the problem in factoring into something similar to a cyclic group. A cyclic group with some period. And then we show how quantum computer can find that period. Now, with lattice and code base, now we are moving to a different direction. We are now mixing algebra and geometry, which is beautiful on its own, right? If you look at code-based cryptography, what are we using? We are using vector spaces, subspaces. What is special about that? You have bases. But if your dimension goes bigger, you have so many choices for bases, right? So you can choose a basis that looks good to you, but looks bad for your adversary. But you can hide the transformations. That's your key. I hide the transformations. You're not going to see my transformation ever. And then after that, what do? You put poison into it. You put errors so that it goes haywire. So that whatever algorithm is being applied to that, quantum or classical, it cannot catch the original structure. But you can do it. Why? Because you know how to error correct. In the lattice versions, you know which one is actually the shortest vector within a particular basis system. If you change the basis, the shortest there may not be the shortest anymore. So now you're shifting the perspective into a combinations of geometry and algebra. And there, Shor algorithm is powerless. So that's my first question, what I know. Okay. So now what I don't know, and nobody around me also seems not to know, right? Including Peter Shor. Actually, Peter Shor wrote a paper about it. He said, after my discovery and Grover discovery, there does not seem to be any advanced cryptanalysis from quantum anymore. If you follow the development in quantum cryptanalysis quickly, okay, you read the papers accepted in Eurocrypt, Crypto, AsiaCrypt, PKC, and so on and so forth. You look at them, their gain is very small. or you need to do a lot of effort and the gain is super small. It's a nice technical paper. It gets accepted to all these big conferences, right? You get published in the top journal, but essentially it doesn't affect much. There are a lot of work like that, including mine. Very nice technically, but okay. Doesn't affect real situation much. So Peter Shaw is thinking, why? So apparently there are limits also to the power of quantum computer. There are limits. But where? Which one is the limit? We don't know yet. So I know my answer seems philosophical to some of you, but that's what we are. At the moment, that's where we are. Okay. So yeah, there. So okay. So here is what I'm going to go through with you. I'm going to go by parts. Okay, by parts. I'm going to skip some of the technical computations because they're there. Okay. So really, I'm not lying. I was not lying to you when I said that you have elementary number theory. You can go through this. I'm not bluffing. It is true. Okay. So here, I'm going to switch this problem from factoring into order finding. So this is the most important step. This is the main insight. Actually, this was not due to Shaw. Somebody else understood this before. Simon. The name is Simon. If you read in the literature, Simon algorithm is not as famous as Shaw algorithm, but Shaw actually borrowed from Simon. And Shaw acknowledged it. Okay, so I'm not saying that Shaw claimed this to be his own. No. Shaw know about this, and he put it into the context, into the proper context, and that's the amazing part of Shaw paper. So he says, okay, so let's say without loss of generalization, we assume n is odd. I will mention about the case when n is even later. But in the context of RSA, our n is odd, right? N is p times q, p and q are odd primes. Okay, so n is odd. Anyway, so that's the main reason why we use this. But the Shaw algorithm works for any number, so even the even one. Okay. So suppose we find a solution. So here, big suppose. Suppose we find a solution to this question. So the problem says, find me an x such that x squared is 1 modulo n, but I don't want x to be 1 or n minus 1. Why? Well, if x is 1, it's done. If x is n minus 1, it's also done. You just plug it in, it's solved. Right? Those are trivial solutions. I don't want trivial questions. I don't want to solve trivial problem. What happened to my connection? Oh. Somehow my connection dropped. Oh, it's okay. I'm hotspot. It's okay. All right. Back alive. Okay. So, and now I'm going to write that one as this one. That's clear, right? From 1 to 2, 1 and 2 are equivalent expressions. So now I'm writing x squared equal to 1 modulo n as x squared minus 1 is 0. And I'm splitting the x squared minus 1 into x plus 1 and x minus 1. Okay? So what does this mean? This expression means n has a common factor with x plus 1 or x minus 1. Now this common factor cannot be n by the exclusion here. If you're not sure about the details, leave it, trust me. Later you digest it again. Okay? So this common factor is not n. Therefore, the GCD of x plus 1n or GCD x minus 1n divides n. What happened here? What happened to my sharing? Oh, actually my Zoom dropped. Okay. Now we are back.
We are still here to account.
Yeah, strange. Suddenly it drops. Okay, anyway, we have time. It says here my internet connection is unstable. I'm dropping again. As a backup,
To try to tackle.
oh, it's actually okay again. Okay, so now this common factor is not n by the exclusion. Therefore, we know that the GCD x plus 1n or GCD x minus 1n divides n. So what does this mean? Let's backtrack again. Yeah, we look at the suppose. Suppose that we find a solution to x there. So we find x such that x squared equal to 1 modulo n. Okay. Now we write x1, this expression, as that expression, which is okay because we excluded this two. Okay. Now that means here n, this is 0 modulo n, right? That means either this or this will have a non-trivial factor common to n. That means the GCD of this and n, or the GCD of this and n, will be non-trivial. Okay? Will not be 1 and will not be n because of this exclusion. So what does that mean? That means we have found a divisor to n. Again, we have found a divisor to n. But again, look, this one is suppose. Suppose. So then we need to show that this can be done with high probability. So that's the key. But this is the thinking behind it. If you can find such an x, then you can find a common factor with n. That means you can divide n non-trivially. Okay? So that's a setup. If you can find an x with this property, that means you find a divisor of n. The next question, can it be done efficiently? There is a follow-up question. Can we find such an x? So then now the next step is we look into the probability of finding such an n. Remember, quantum mechanics is probabilistic. Shor algorithm, Shor in the abstract says random, efficient, random. Okay? So this is very important. If you remember only one thing from this lecture, this one. You forget everything else, I consider my session successful. You understand this? That's the foundation of everything else that we are going to go through. Any question? You want me to explain again? I will explain again. This is very important. Now, probably some of you who like number theory will start saying, so now we are going to center all our attention to that x. Yes, we're going to find that x. And we will show that the probability is high and that we can find it quickly. Okay? But now I'm going to insult everybody around here and review Euclidean algorithm. Okay? Everybody have heard about Euclidean algorithm, right? Okay. I'm just going to highlight certain things here. I know everybody knows how it works, okay? Even Elementary school kids, some of them, the bright ones will know this already. At least they've tried it. All right. So if A is greater than B, A and B are integers, we assume positive, okay? We don't deal with negative integer and stuff like that, because here is factorization in the integers, okay? So then I can write A is QB plus R. Now I can write R as A minus QB. Then I can say that if I'm looking at the GCD of AB, it's actually GCD of BR. So of course, R is now smaller because this is the remainder. The remainder is smaller than B. Yes, we agree on that. So GCD of A and B is actually GCD of B and R. And then I can continue the process. B and R, you can do it like again. And the number will keep going down, going down, going down, until at the end you have R equal to 0. Yes? Okay, good. Everybody still know Euclidean algorithm. Okay, so we terminate at R equal to 0. So this terminate. The next question is how efficient? How efficient? We know from experience, we do it by hand, it's efficient, right? You do it by computer program, it's super efficient. You just borrow from Python library or from C library. It's very efficient. But let's check at the running time. The running time is at worst. So the worst that will happen, the running time is log 2 of A. So your input A, the log 2 of that A. So if A is 20,000 digit, we just need 20,000 steps. So this 1,000 step is nothing for computer like this. Okay? Now we have what? Processor, common processor is giga. So 20,000 done. Okay? So here, it might be turned into a question, multiple choice question. The remainder R is always smaller than B over 2. Why? I will let you decide why. The key is to look at B. Is B bigger than half of A or smaller than half of A? Then you will know the answer. Okay? Your homework. But this is easy. Very easy. Now, back to short algorithm. Again, it's so important I repeat it again here, right? So we can factor n if we can find x squared equal to 1 modulo n. So now, here is the random part of short algorithm comes in. Let me choose a random number, IID, okay? IID, meaning it's really randomly chosen. You're not, you're not more inclined to choose one number over the other. All the same probability. Okay, IID. You take a randomly chosen number between 1 and n minus 1 exclusive because we exclude 1 and n minus 1. And now, if we find this, then of course, since Euclidean algorithm is very fast, I can check the GCD. If the GCD is not 1, then we are done. We found the factor, we continue the process. If it is 1, then y and n are co-prime. Y and n are co-prime. What does that mean? Y is a part of the set of all numbers which are co-prime to n. Right? We usually denote that with a star on top. And that set is actually a group under multiplication, yes? So at that point we are clear, happy, everybody, okay? It's a group, okay? You collect all of those co-prime numbers to n, collect them, you put an operation multiplications, it becomes a group. Right? So, now, we're talking about order. The order of y in this group is the smallest integer r such that y to the r is 1. So here I'm already assuming there is a cyclicity here. It's clear, right? So you have y raised to 0, which is 1. You have y squared, y cubed, and so on and so forth until you hit the first. This actually is smallest positive integer. I don't want 0. You can add yourself positive integer. Okay, such that this happened. Because it's a finite group, This must happen. If this one never hit 1, then that group is not finite. So you have a contradiction. That's very clear. Okay? So if R is even, then we have a solution already. So that's our X. Our X is Y raised to R over 2. Beautiful argument, right? Completely elementary. Everything here, nothing beyond first course in number theory so far. The problem is, how do you recognize that argument? How do you get that idea in the first place? Now that they don't teach you in any course. You don't learn that in any course. Okay? Nothing really fancy here, right? Everything is so clear. So here is the most crucial observation. This is the most crucial observation. If we can show that the probability of a random co-prime number y whose order R is even is high, then we have reduced the problem of factoring to period finding. Okay, I see some blank faces. Let me go back. It's okay not to understand at this point. So now you have this group n star. Let's call it n star. Okay, you have this group n star under multiplication, and now I'm picking a number from it at random. I choose y. Now, of course, this group y has an order. If this order is even, then I actually have found a solution. That's my solution. Okay? So now the question is, how do you find this y? How do you find such y? How many such y's are there in that group? That's the issue now. Okay, the issue is how many of these y are in that group. If the probability, if the number of such y is many, okay, if the number is big, you divide that by the phi of n, it's big, then there is a high chance of you picking it up. When you say, take a random y, okay, then your success probability is high. If, for example, you have 10,000 number in there, but only one satisfies this, then you are in trouble. Because you need to check everything, and if you're lucky, you get that one. If you're not lucky, you repeat the process from the beginning. So now the key here is, how many are there? And what we are going to show is that there are many. So if there are many, therefore, you don't need to do this so many times. And therefore, you can solve it efficiently. Because every step of this is efficient so far. We don't see anything which is not efficient, right? Everything is efficient here. So I hope it's clear.
Sorry, sir.
Yeah.
About if R is odd number.
Yes, we are going to see how many are the even one.
Oh.
So the y here is not independent of R. So the y must be chosen such that the R is even. Because if R is odd, no gain. We don't have anything. Then what happens if R is odd? Throw it. Choose another y. So that's what I'm saying, that this y must be many. And this y must be easy to find. Otherwise, you have a nice theory, but you cannot compute. So that's the point. Nice theory, cannot compute. Can submit to nice journal, but not computational journal. Okay? And then maybe you can do analysis, what is the probability and so on and so forth. But that's not interesting for us right now. Okay? So you see, you need to find y. Once you get what y is, you need to check, okay, the order is even, and then we are game. So that's the genius of Shor, actually. Shor did an analysis, what is the probability and how we can proceed with that. Good, any more questions?
So if it is just finding the coprime numbers on the n, so what's the difference with try factoring n with that numbers?
Well, we did try. We have found the factor. Now, if you're looking at the coprime, how do you factor it using just the number? You have a number which is coprime to what you want to factor, and then how you proceed. In this algorithm, the way to proceed is let's look at the cyclic group generated by that component. Okay, let's look at the cyclic group generated by that component and then see if we can actually use that information to find X. Remember here we are putting our hand on Y, but not on X yet. So if you just know Y, it's not enough to solve for X yet. Okay. So here, I hope I answer your questions. It's not like you can. Okay, what happened? It's not like just okay. I choose any number which is coprime to n, and then the next question is what do you use that number for? How are you utilizing it? How does it give you a benefit? Here, the benefit only arises when you can find an even order, and when you can find the even order, then you can translate the problem well. Then you change the original problem of factoring into a problem of order finding. Okay. Now, classically, these two problems are equally hard. Classically, these two problems are equally hard. But in the quantum setup, the equivalent problem, the problem of period finding, becomes easy. So that's the main difference. Classically, you want to find the order, what do you need to do? Discrete logarithm, right? But discrete logarithm is harder than continuous logarithm. Continuous logarithm, you can use calculus to find convergence. You can bound it, you can find convergence. When in the discrete case, there is nothing to converge on because there is no neighborhood. There's no neighborhood, you cannot converge. So here, the problem, is this problem known to number theorists before? Yes. It's just that it's not being utilized. Because this translation into period finding is known to some specialists. The problem is, then what? Now, in quantum setup, this one can be done efficiently. So that's the key. All right. So now the next question is this, right? Randomly chosen Y has an even order R with high probability. So that means if you fail, you try one more time, you fail again, you try one more time, your chance of actually hitting a result is high, getting higher and higher, higher. In fact, you can compute the expected number of try until you get an answer. And that expected number is small because the probability is high. Okay. So there are many of such number. If the first time you fail, try again. Your chance of hitting the correct one increases. Can you just load the? Or okay, let's see. All right. It's okay. It's a minimum disruption. It's not. Gak apa-apa. It's just sometimes the internet connection just suddenly. It's okay. So now let's start. Let's start with the easy one. So n is an odd prime. Okay, n is an odd prime. That means what? N minus 1 is even. Then this argument is actually very easy. I'm not going to go through all the details, okay, but just a step by step so you know how to do it yourself later. So n minus 1 is even if n is an odd prime. And then now I'm saying, okay, this n minus 1 is even number, right? So there must be an m which is the highest power of 2 that divides it. Because then you can express this n minus 1 equal to 2 to the m times some odd number. What is that odd number? I don't know. And at this point, I don't really care because we want the order to be even, right? So the group is cyclic, we know. Now I can write y to be some g raised to t, for some generator t, because it's a cyclic group. So there is a generator. What is that generator? I don't know. Some generator. There must be. So now, instead of writing it as y, I'm writing it as g raised to t. Okay? So, case 1, t is odd. Then I can easily raise g to tr modulo n is 1. Why? Because tr divides n minus 1. It must be. R is the order. So t being odd implies 2 to the m divides r. What does that mean? R is even. Right? Divisible by 2 to the r, to the m. So that's okay. This case is fine. Not a problem. We are okay. So here, look, from y, you need to find g. You need to extrapolate g. But typically, why don't we just choose g and check with generate? So there are many ways in here, but the main insight is that when t is odd, okay, when t is odd, you're fine. What happens when t is even? Well, you do the same thing. And now you see here, when t is even, our analysis says that r is not divisible by 2 to the m. Okay, it's not divisible by 2 to the m. So what happened here? If n is an odd prime, with the property that 2 to the m is the largest power of 2 that divides n minus 1, then exactly half of the number in that group will have an order which is divisible by 2 to the m, and the other half doesn't. So now the probability of getting an answer is half. So the expected number of trial is small. You fail, you try again, you fail, you try again. Half of this will be a feasible answer. What will happen? Well, expectedly, if you do it twice, you must have something. Of course, you can find the standard deviation and so on and so forth. But even if you're very, very unlucky, you try 10 times, you must have gotten it. Okay, so that's my hand-waving analysis of this. If the probability is half, you're bound to hit it. So, okay, so it's good for our purpose. But we want to know what happens for general, not for just n is prime, okay? In fact, RSA, n is a product of 2 primes, right? So let's look into that. But before we go there, let's look at n equal to p raised to alpha. P is prime. For now, we assume n is odd, right? So p must be odd. P cannot be 2. Actually, if you do the analysis, you follow your algorithm explanations, this can also handle that case, but it's not of our interest today. I put a remark later on. Okay, so we repeat the argument above. Homework. But it's not difficult. I'm telling you, it's not difficult. I don't like to torture my student unless I have to. But the argument is very, very similar to this. Very, very similar. You replace now n minus 1 with something else. Okay, you replace n minus 1 by this. That argument above works exactly. So you say, okay, so now I'm choosing a generator G, and then now I look at T, and T is odd, what happened? And T is even, what happened? Exactly. Same analysis.
Yeah. How to find G?
G, we don't really need it. G can be anything. For the purpose of our analysis, we don't need it, because what we need is how many. We just need to know how many. Here, we don't really care to find which one. Because if the probability is half, you don't really mind. Just try. Anyway, the expected number of trial is small. Say you fail, throw it, get a new number. You fail, throw it, you get a new number. It cannot be that you go on indefinitely without getting anything. So that's the main. So really, we don't need what G is. Okay, so the conclusion is the same. Exactly half have an order which is divisible by 2 to the m. The other half don't. So probability half. Whether it's prime or a prime power, is half. Half of the set of coprimes, group of coprimes. Okay? So then we go to the general case. Now here, you need Chinese remainder theorem with it. But in principle, it's the same analysis. Just a little bit more fine-graining. Because now, if your n is something like this, so P1 alpha 1, P2 alpha 2, Ps alpha s, what happened is the same. That one is a group, a direct product of the prime factor cyclic group of this number. Okay, so then the analysis is now inductively done in nature. You start with this first, use the result from above, because this is the result from above, right? See some blank faces. Let me repeat again. Look at the step by step. Okay, don't worry about the detail first. Don't worry about the detail. You can work the detail later. We start with n is an odd prime. The conclusion, half of it is okay. The other half, we don't get any. So let's move on. N is p raised to alpha. We have the same situation here. Here, you can think of it as P1 alpha 1, and everything else is 1. Okay? So that's the case. So we have it. We have the same result, the same conclusions, and now when we are looking at this, look, these are all co-primes, right? These are primes. So you can use Chinese remainder theorem. Agree? Agree? So you know this structure actually from Chinese remainder theorem. Okay? I'm not going to teach you algebra at that level. We don't have time. But at least you know that this is Chinese remainder theorem. Plain and simple. And now I'm looking at this one by one. I look at the operation there, one by one. Now I'm splitting it into this. Okay? So here I put the analysis. I'm not going to go through details for it because I do want to go for the next step. But the process is just a fine graining of the analysis in the second case. Nothing very magical there. Just Chinese remainder theorem and proper accounting. That's it. Right? So we have cases there. And I said that, well, for this case, we need to worry about something. For this case, we don't need to worry about anything. You can go through the analysis. I've put them down there. The key is here. This is the conclusion after you do that analysis. Okay? Yeah, I think people still have a rather good energy level. I'm okay with that. So the probability that the random number x with GCD xn equal to 1, the order is r, is even, and this x to the r over 2 is not equal to -1 mod n is this. This case is the case where we don't need to worry. We do not need to worry about this case, and this is the explanation. So at the end of the analysis, in the most general case, n equal to P1 alpha 1, P1 raised to alpha 1, P2 raised to alpha 2, and so on, Ps raised to alpha s, the probability is larger than this. 1 minus 1 over 2 to the s minus 1. So you see something nice here? This is actually intuitively correct. I mean, if you think about it, if a number n has many prime factors, what does it mean? It's easier to find the factor, right? Because there are many, right? That's why for RSA, we stop at 2. And these are all primes. So we don't have like P raised to something times Q raised to something, because that will make it easier for the attacker, in fact. So here the analysis says, the more factors you have, the probability of finding this number X is actually almost 1. Okay? So intuitively, our conclusion matches with what we experience. Now, in RSA, S is 2. So what is the probability? It's 1 minus half. So at least half. So when we attack RSA with this, we are good. We can do that, right? Because let's say if this probability is very small, let's say epsilon, okay, 1 over something, 1 over 2 raised to something, we are in trouble. Because we know how to translate the problem, but finding a solution is extremely low in probability. So that means, will the algorithm work? Yes. Will it be efficient? No. And that means, well, you don't have advantage. You use quantum computer, but you don't have advantage. So there's nothing to do. So why make your life so difficult without any gain? Right? Now here, because of this, then we have two conclusions. It is sensible to reduce factoring into order finding because it can be done theoretically, and computation-wise, it's fast. Okay? Everything we have so far is just Euclidean algorithm. Amazing, right? It's a very old algorithm, very efficient, but we use it. So sure, it's actually just borrowing from Euclid and Simon and Fourier transform. Yes, true. He borrowed from all of this. But his genius comes about because he can stitch them all together. We all know so many theorems and so many techniques, right? But we may not know how to connect them. Sure, see all of this very simple thing, nothing, well, it's nothing very difficult, right? So far, nothing will make you bleed in the nose, nothing. It's super simple, all of them. But we settle this. So I mentioned here there are several minor possible cases, okay? But for that, there are even classical algorithms. You can see Nielsen and Chuang textbook. Michael Nielsen and Isaac Chuang textbook in quantum computation. They discuss this. So let's now accept that we can do this. And now we change the factoring problem into this formal problem statement. Given xn such that the GCD is 1, find the smallest integer r such that x to the r modulo n is 1. Actually, at this point, we can stop. Because now you know how to turn this factoring into efficient period finding. If you have quantum computers of that scale. Okay, I'll stop here briefly and answer your questions. So if you can find this, you can factor. Okay? So that's the first step, which is the big step. And this is actually, in fact, the hardest to explain to people who don't have number theory background at all. How do you go from there to here? Okay, spend 1 semester, learn number theory, then come back to me. After that, I'll explain.
Yeah.
what happens if a unit group Zn star is not abelian?
But in this case, it's always abelian, right? But for example, you move to another integer set, like let's say, I don't know, Eisenstein, whatever. It's still abelian, right?
If we have a group not abelian, replace Zn, why?
Well, if you have non-abelian, then it might not be vulnerable against Shor algorithm. But if you want to turn it into crypto system, the next question is it better than other in terms of efficiency, in terms of security? So yes, actually, Hati here caught the essence of this, which is precisely connected to Pak Uha's question earlier. Then how do we know that if you choose other system, other mathematical system, it will not be vulnerable against quantum attack? What he's saying, well, all of these are abelian, right? In fact, this is stronger than abelian. This is cyclic. The cyclic it has more structure than just abelian. So the next question is what he's saying, why don't we move it into some non-abelian group? Yes, that's precisely what we're doing. So if you look at all of the other proposals for quantum secure, they get rid of the abelian. In fact, the first thing that many researchers look into was, can we use dihedral group? Because dihedral is like, it's almost abelian, right? Almost. At least if you look at the subgroup that contains only of rotation, this is abelian. Once you put the reflection, that the whole thing, the abelian part is gone. So in fact, there are quantum algorithms that attack dihedral, but not as effectively as Shor. Not as effectively as Shor. Okay. It's nice, it's beautiful. If you look at the transition of the problem, I hope at this point you get some understanding what's going on. Okay. I don't have much time, 15 minutes, so I will go briefly through what the next steps are. The next steps are not as exciting as the first step. I mean, I'm not saying they're bad, they're technical, but it's not as elegant as the first one. Because that move from factoring to period finding is really what blew my mind the first time I actually understand this. I was like, whoa, okay. So the next one are less impressive, okay, but nonetheless they're powerful. So I will go through quickly through them. Part 2. Here comes the truly quantum part of Shor algorithm. Okay. So here, Shor uses quantum Fourier transform to perform this thing called phase estimations. Okay. Again, as I mentioned, this is out of scope for today's discussions. But remember, this quantum Fourier transform perform phase estimations. So, what does this algorithm produce? This algorithm produces an estimate. Look, this is probability. When we deal with quantum mechanics, everything is probabilistic. You never get the exact answer, except in trivial cases. So everything is probabilistic. Now, what is this phase estimation giving you is an estimate of a random, look, it's already random and then now you estimate it. Okay? It's an estimate of a random S over R. This is R is what we want, right? This R is what we want. But what we have is a random S over R for some S here, some. So the S, which one is the S? I don't know, one of these. It's chosen randomly. So just remember this phase estimation gives you an estimate of this. All right? As I mentioned, this is another lecture. We'll probably need to go back into the bra and cat notation, the qubit, the quantum ensemble, and so on and so forth. Maybe next time. I have the notes if you're interested, but let's not get distracted too much there. Now, after we get that estimate S over R, we still need to find R, right? Because R is what we want, not the estimate of S over R, where S is random. So the next step is we use this continued fraction algorithm, okay, to find R from that estimate of a random S over R. Okay. Now, this is crucial. The observation S and R are bounded integers. Bounded. Why? Well, R is bounded. The group is finite. So R is bounded. Now, S is bounded. S is bounded. So we know S and R are bounded. That means what? S over R is rational. If it is rational, of course, it's real. If it is real, you can estimate using continuous fraction. We have an expert in continuous fraction here. A few others. So, but I tell you what, continuous fraction is just Euclidean algorithm. Okay. Okay. So what is continuous fraction? It's just a representation of a real number by a sequence, possibly infinite. The sequence might be infinite. Okay. So there you know, this is how it looks like. Then there are several insights. If we allow A1 to be 0, then any element in N will have a continuous fraction expansion which converges. So the connection to that estimate, we can make that estimate converge to a definitive answer. But for this to converge, you need to satisfy certain conditions. And therefore, that phase estimation algorithm needs to be run multiple times, not just one time. And there you need the analysis of how fast can you do that, and so on and so forth, okay? So here, so this continuous fraction algorithm finds this converging expansions. Confused? That's okay if you're confused. It's not something that that used very often, but you see, continuous fractions are actually already known to the ancient Egyptians. They already used this. So it's not exactly new invention. It's just that you can use the old algorithm to settle this. But this is what I want to tell you. This algorithm is actually just modified Euclidean algorithm. It's just a modified Euclidean algorithm. So how does the continuous fraction algorithm work? So let's say that rational number is P over Q. And since I'm lazy, I just write diff to means integer division without remainder. So when I say diff, that's the whole part component of the. So if you look at GCD of AB, right? I mentioned this will be QB plus R, right? So that Q part is the whole part here, okay? So now you look at this, right? Now I apply the first step of Euclidean algorithm. I can write this P over Q as P diff Q plus P mod Q over Q. If you expand it, you will see that this is true. It's like Euclidean algorithm, really. It's just that now you sort of invert it. You look at the fraction instead of the whole thing. Now, I express this as this. It's actually just a sleight of hand, right? I'm writing this as P mod Q over Q as 1 over Q. And this, I put it in the numerator here. It's nothing fancy. Just rearranging the term. Okay, so now I continue like in Euclidean algorithm. I continue with this. I continue. This is Euclidean algorithm. That means this is efficient. This is in fact faster because we are dealing with fractions. It goes down faster. Okay, nothing really exceptional. Just you need just to look at it from a certain perspective. Then you see, oh, okay. So it's just that. Nothing fancy. So this conversion is of course follow from the convergence of Euclidean algorithm. The running time is small, so you can quickly find your convergence. So how do we benefit from this CF algorithm? Okay, so let X be a rational number which approximates some reduced fractions. The question is, how close does the approximation needs to be? Remember that S over R as the output of the phase estimation, the quantum phase estimations, is about estimate of a random S over R. S is between 0 and R minus 1. So now, we need to make sure the condition required for continuous fraction expansions to contain the continued fraction expansion of P over Q. So here is intuitively what happened. You have the estimates of S over R. What you want the exact S over R. How do you get that exact one? You need enough samples of this estimate to be able to create some neighborhood where then you can say that's the value we want. So you need to run the phase estimations a few times. I write down the process here. This is calculus 1. Okay, the first course in calculus, nothing more than that. The same neighborhood analysis. Okay. Continue. You just continue looking, refining your neighborhood, okay, until you find how many after log 2q iteration. You remember this expression from Euclidean algorithm? Log 2 of k. Here, log 2 of q. Remember, this is p over q, so now you're looking at the denominator. Whatever that denominator is, that's the worst you need to do. Are we done? Well, theoretically, from this convergent analysis, we are done. Because this convergent analysis basically says, you use continuous fractions, with enough number of samples, you can pinpoint what that S over R is. And therefore, you know what R is. And therefore, you find X. Okay? Now, are we done? Not yet. Because we need some, we did some hand-waving argument, right? Because I skipped that quantum phase estimation. There is something there in that quantum phase estimations that is needed for this continuous fraction algorithm. How many approximations of S over R you need to find this number? You must run that phase estimation at least this many times. But look, this is efficient. Let's say your N is an RSA public key, which is P times Q, and you use RSA 4096. Right? So that N size is 4096 times 2, right? The size of this number. If you take the logarithm, this is actually still small. It can be done efficiently. So you don't just get one phase estimate of S over R and then you're done. No, you must have these information to ensure that you can pinpoint that S over R. So are we done yet? Not so fast, not so fast. Wait. There is one last step. Let me recap. We use the order finding to produce an estimate of S over R. This estimate is the one done by the quantum phase estimation algorithm, which is the properly quantum part of Shor algorithm. Now, what if S and R actually share a common factor, meaning they're not in the simplest form? When S and R over R is not in the simplest form, what happened? Remember, R is the smallest. It's the order. The order must be smallest. So now if they have a common factor, this actually is not the smallest. We can still get the wrong answer. The R that we get from that continuous fraction algorithm can actually be, it's not the order, but some multiple of the order. So how do we get rid of that? Okay. If you read Shaw paper, Shaw has a very nice analysis on how to make sure it is done, blah, 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 blah. But then other expert pointed out, there is actually a much simpler way of ensuring it. It's a bit more expensive to do computationally, but it's a lot simpler. So that's usually what's being used. Okay. So now, if S and R share a common factor, what we are actually looking for is this R prime, when this is in the smallest form, right? Okay. So now, we need this estimate, not this estimate. But how many times is this happening? That's in the Shor paper. Shor analyzed what is the probability, and this probability is small, and therefore you can bound it, and you can get it out of your system. So that's the argument in that. But there is a nicer argument. Run the algorithm twice. If an algorithm, the entire Shor algorithm, is efficient, you do it 2 times, it is still efficient, right? So in the Shor original paper, it says you need to do the following to trim this problem. But the solution, a simpler solution is, no. Don't build another, don't build another routine to perform this. Just run the algorithm twice. And from this running it twice, you just take the LCM of the 2R. So if you run it twice, you find 2 S's and 2 R's, right? 2 S's and 2 R's. So then you just choose, if the 2 R's differ, if the 2 R differ, so R1 and R2, if they differ, use the LCM. Okay? If the 2 S's are co-prime, then the LCM is the correct R. So the probability of this happening is 3/4. So if you fail, you do this, and your chance of succeeding is now 3/4. So you're fine. So at this point, we are really, really done. You find R, you solve that order finding problem, you can factor. Okay? So this is the story of Shor algorithm. That's it, I'm done. Any question? Heavy? Oh, well, it is quite heavy, but also it's a very nice algorithm. And since we are all, I assume at this level, if you reach this level, you're not afraid of technical argument. I think it's worth reading if you want to go through. Or you go through my notes again, work on the details yourself, and then try your hand on the actual paper. I always say you read the original source. Okay. Now I'm going to just spend 2 minutes on these concluding remarks, if there is no questions. This is actually an aside from what I already mentioned when I answered Paul's questions, right? So we do not yet know of the exact relationship between the complexity of quantum computer and the classical computer. If you read news, if you read some expert talking for the public, there's a lot of simplification being offered. But actually the real situation, we don't know. We don't know the separation of quantum supremacy. Are quantum computers really much more powerful? That's still not very clear. And that's good, because like Feynman said, by golly, it's a difficult problem. So still, 40 years after Feynman said it, it's still true. It's not easy. So, but what does Shor algorithm tell us? That indeed, quantum computers have some advantages. It has advantages. Because that phase estimation cannot be done in a classical setup efficiently, but quantum can do it. Okay. So the so-called quantum supremacy is not as general as typically presented to the public. Now, some people will say, well, then we are not doing too bad with our digital computer. Yeah, we are not doing too bad. We are quite okay, actually. But there are some stuff that quantum computer can do, we cannot do classically. And for that stuff, maybe then we can gain something. And here I want to branch out a little bit from cryptography. The use of quantum computer in cryptography is just a small subset, because quantum computer can also help simulate weather. It can do a lot of nonlinear analysis. It can perform stochastic analysis in way beyond what the classical computer can do. Okay, so it's much broader, and a lot more to investigate. The first one is very difficult question in engineering. Can you actually build a large-scale quantum computer? At the moment, the answer is not clear, because theoretically we can, but saying that theoretically we can is very different from making it happen. Now, many people say it will be too difficult. We are never going to reach that level. I will be a bit skeptical about that, because many people have said something like that when we deal with transistor, when we deal about how to build a microelectronic and everything, right? People say it's never going to be done, and then somebody did it, and then it's done. So I don't want to say much about the future. I don't know about the future, but hopefully, we gain some understanding of what the situation is. So a lot more to investigate. Good for you. More problem for your advanced studies and postdocs and whatnot. Okay, thank you. Thank you very much. Yeah, I think it's heavy. Everybody tired. I'll make you even more tired later.